So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video. Well, what? Okay, I think it's been a long day, which for which we have talked, but now I'm fine. Actually, I was giving some exams, so that's why I was like involved in those kind of things. But now I'm free and just looking for some results. Okay, it's all right. Okay, so basically today we are gonna dive into a crazy thing. Like, I have uploaded almost 72 videos right till now, and I haven't discussed these things. And you know what? My YouTube channel is of higher mathematics, and if we haven't talked about this thing yet, so it's quite weird, right? Because this is the Gaussian integral. Whoa, look at this integral. This integral is known as the Gaussian integral, and this integral is crazy, mind-blowing, amazing, interesting, and a lot of things. This is the most elegant integral. You know what? If you're gonna search out on web that the most crazy integral, the I would say the most interesting integral, the most elegant integral. So you're gonna find this integral, maybe ranked at one or two or three, but there are a lot of more like options, like the derivative integral, which we have proved I think two times in my on my channel, and you can check that out if you want. But now let's just check out this integral. And you know what? Why I need to just discuss this integral here? Because I have derived or have discovered something using this result, and I just want to use the result of this integral. So I was like, we cannot discuss that thing directly because we don't know about the Gaussian integral. So for firstly we need to care about the Gaussian integral, and then we will just move to that result that I have found. And that result is crazy, like amazing. So I would like you to just watch this video till the end, and then just come up for the next video, because that is really amazing. So now let me just tell you that what this integral is. So it's the integral from negative infinity to positive infinity of e to the negative x squared, right? Okay. Now if you're gonna do something like what we do in our daily lives, like use sub or by parts, or something by partial fraction, although it's not working there. So these kind of things ain't gonna work at all. So how we gonna do that? Well, I'll tell you in a while. And you know what? The result of this integral makes this integrals even more crazier. You know what the result is? It's the square root of pi. Oh my goodness. Look at this integral and its result. This is known as the classic elegant integral, that is the Gaussian integral. Now let's talk about the proof of this. Okay. So basically we are having I equals integral from negative infinity to infinity of e to the negative x squared dx. Well, since x squared is an even function, so we can write this as 2 times integral from 0 to infinity of e to the negative x squared dx. Now let's talk about this integral. So I would say this I naught. Okay, so basically our I naught here is integral from 0 to infinity of e to the negative x squared dx. Okay. Now, you know what? Since it's a definite integral, and we can just replace this x and this x with any constant or any variable, that is, let's just replace that with y. So we can do that. So I naught equals the integral from 0 to infinity of e to the negative y squared dy. So this is your first equation, and this is your second equation. So we are going to talk about the multiplication of the first and second equation. That is I naught into I naught, that becomes out I naught squared, and integral from 0 to infinity e to the negative x squared dx and times integral from 0 to infinity of e to the negative y squared dy. So this is I naught squared, right? And this is gonna be a double integral. So the integral from 0 to infinity and the another integral from 0 to infinity e to the negative x squared times e to the negative y squared dx dy. Now you're gonna ask me why we are doing that much amount of things, because we just started from this integral and we are here with double integral. So like, why do we need to multiply that? Well, wait, don't worry. So I naught squared, and further we retain something like this, integral from 0 to infinity, actually double integral, and we can write this as e to the negative x squared plus y squared dx dy. Wow, that's good. And now comes the amazing part. And you know what? I think this is the easiest derivation or easiest proof of the Gaussian integral, or the easiest evaluation of the Gaussian integral, because we just have to play with some two definite integrals, and then we have to just multiply them, and then we just have to use a u sub here. And what's the u sub? Well, there are a lot of ways by which we can do perform this integral, like the Feynman technique, or the complex analysis, or the polar coordinates, or a lot of things, but this is the most easiest, I think. So this is I naught squared equals integral from 0 to infinity negative x squared y squared dx dy. Now let y equals xt here. This is the key substitution here. So y equals xt. So dy is gonna be x dt. X is a constant. We are considering x as a constant. And the limits ain't gonna change, right? So basically we are talking about this. Oh, I think I should consider dy. Well, due to linearity we can say that. So I'm talking about this integral. So I naught squared is gonna be integral from 0 to infinity, and then integral from 0 to infinity as well, and it's e to the negative x squared, and y squared is plus x squared t squared, and right, and your dy is x dt, so it's x dt, and then we are having dx as well here, right? Okay, now let's do something. And now you know what, why we did that? Because to make something factor of x here, and now we are good to go with our basics of integration, which we can do that. Again, a u sub here, but before that let me just write it in a manner perfectly in a manner. So it's I naught squared integral from 0 to infinity, and it's x e to the negative x squared 1 plus t squared. I have factored out x squared from this parenthesis, and we are having dx and dt, again due to linearity. Okay, now let's talk about this integrand. Okay, basically I'm talking about this part here. So if we talk about, let x squared actually, let x squared 1 plus t squared equals, let's say, z, right? So if we talk about the derivative with respect to x both sides or z both sides, so it's 2x and then 1 plus t squared. This would be considered as a constant, right? And it's dx equals dz. So if we talk about x dx, so it's dz over, it's 2 times 1 plus t squared. Now we can just replace this x and this dx with this dz over 1 plus t squared, 2 times 1 plus t squared, right? Now let's integral from 0 to infinity, and again limits ain't gonna change. When you plug infinity here, so z is infinity, and when you plug 0, z is 0. So it's double integral again. and we are having x dx is, well, it's e to the negative z, right? Okay. Yeah, e to the negative z, and then we are having x dx is dz over 2 times 1 plus t square. Well, don't worry, I'll just write this down again here, and we are having dt. Okay, now let me just write that down again on the board. So yeah, this is, well, you know what, this is one of those integrals which are really difficult to evaluate, so we have to go through these kind of things. So basically, I naught squared equals integral from 0 to infinity, it's e to the negative z dz over 2 times 1 plus t squared, and it's dt. Okay, now I naught square is, we can write this as integral from 0 to infinity of 1 over 2 this factor, and 1 over 1 plus t squared, and times integral from 0 to infinity of e to the negative z dz, and then dt. Right, we can write that, because if we talk about this integral, this is being like integrating with respect to z, so we can consider this 1 over 1 plus t square as a constant, right? So that is why we can write that. So if we talk about this integral from 0 to infinity of e to the negative z dz, this is negative e to the negative z, evaluating from 0 to infinity, and you know what, e to the negative infinity is 0, so this is basically, it's negative of 0, and e to the 0 is 1, so it's negative 1, so it comes out to be 1. It means this integral vanishes to 1, right? And now we are left with that integral only. That is, I naught squared equals 1 over 2 integral from 0 to infinity of dt over 1 plus t squared. Again, a basic integral, that is, it comes out to be arctangent of t from 0 to infinity and over to a factor. So arctangent of infinity is pi over 2, and arctangent of 0 is 0, right? So basically we are having I naught squared equals 1 over 2 times pi over 2 minus 0. So it comes out to be pi over 4, right? So I naught squared equals pi over 4. Now we are just going to take the square root both sides, and we are here with our I naught, and you know what, our I was 2 times I naught. Just remember that. So from here we can say I naught equals the square root of pi over 2, and we had integral from 0 to infinity of e to the negative x squared dx, 2 times integral from 0 to infinity of e to the negative x squared dx, and this was our I naught, right? So basically this is the Gaussian integral. So we can say 2 times this result, that is the square root of pi over 2, 2 cancels out, and we are left with our square root of pi. That's really amazing, guys. And you know what, I can surely say that this is the easiest way by which we can prove this integral, because we don't need to do a lot of things like complex analysis or polar coordinates or some surface integrals. We just have to play with some double integrals, and then we have to just use subs, and yeah, it's pretty cool. It's pretty cool, guys. Oh, so guys, we did that, and if you got to learn something from this video, although you did, so make sure to like, subscribe, and share. And if you have any kind of doubt throughout this video, so you can ask me in the comment section. And I would request you, I would firmly request you to just come up to the next video, because in that video I'm just gonna show you something crazy. You won't believe what I'm gonna show you in the next video. So for that case, you just have to come up in the next video. Thank you so much, guys, for watching this video. Goodbye, take care, love you, and be careful, because life is unexpected. Or maybe that's unexpected. Okay, goodbye, guys. Whoa.